we'll come back with the Hermitian symmetry. So this is how the arrangement is done. Now finally, after combining all the values, we have obtained the final equation as, so just simple mathematics, you see, what you are learning in your signals and systems. So using those simple mathematics, if you open exponential formats, we are obtaining a signal like this. Look at the signal. X of k is your data symbol, and it is multiplied by cos 2 pi n k by n minus x of k is your signal, right? Multiplied by sine 2 pi n k by n. There is no j sign. So because of Hermitian symmetry, actually your summation equation is x of k e power j 2 pi n k by n. E power j means cos plus j sine. But by using this Hermitian symmetry, the signal is now changed into a real format. So like that, there are many techniques available which translates a complex signal into a real transform. So not only Hermitian symmetry, you can employ your own technique, you can make it to a real format. So we invented, my student Kishore, he invented another technique where he formulated a complex signal into a real signal. And also we have tested in the real time. So his work was published in a Q1 journal. You know the Q1, Q2, Q3, Q4 journals, the standard, right? The quality. So the Q1 journals are light wave technology, IEEE, most frequently published papers. So he published 2 papers, 2 concepts into 2 Q1 journals. And this student, my student, she is currently in ATAP. Actually, my overleaf, in another overleaf, I have changed it, but here it is showing. So currently she is an associate professor at ATAP. So this becomes a real signal, okay? So we have some other alternative techniques for yielding a real value signal in optical FDM, like discrete Hartley transform and discrete sine transform, discrete cosine transform, and hardware coded modulation technique, wavelet packet division multiplexing. So many techniques are available. So out of this, one of the technique is Hermitian symmetry technique we have just discussed. Okay, so using Hermitian technique, Hermitian symmetry, and other formats of inverse discrete Hartley transform. Also, we can do the same exercise. So, Hartley transform is directly takes cos and sine format. There is no complex symmetry. Directly takes cos 2 pi n 2 pi nk by n plus sine 2 pi nk by n. This is also called CAS, CAS. So, using that, you can add, you can obtain the signal into the real format. And after that, after making a real, also we have to add a DC bias. Why we have to add a DC bias? Because we have to shift the alternating current, none of the signal to be below 0. We have to add everything above 0. So complex is removed. Apart from complex signal, also we have to make sure that it is always positive. So to make the signal always positive, we add a DC bias. Okay. So the another format of asymmetrically clipped optical FDM, I am not going to discuss more about this. So we do the channel estimation, and so the performance is, so this whole topic is very simple mathematics, very easy mathematics. It has more meaning on it, and so we have tested. So then I'll show another presentation where we see that So I told you a DC bias is added, right? And the center value is 0. And you look at the formation of x1, x2, x3. The other formats are the complex conjugates. Then asymmetrically clipped optical OFDM signal. So here even further, So earlier we used n by 2 carriers. Now we use only n by 4 carriers. So in the n by 4 carriers, what we do, every alternative place we just make a 0. So that is asymmetrically clipped optical OFDM. The another modulation scheme is PAM-DMT. This is a new work. So just look at the PAM-DMT, what we implemented using Universal Software Radio Platform. So this is Universal Software Radio Platform is an NI product, National Instruments product. Now it is taken over by Gates Research. So we bought these instruments. So the advantage of these instruments is the whole of the code of your communication system we write in software. We don't bother about implementation of a modulation, right? Implementation of an encoding, like taking your information symbols. So every concept we write in a software code. Then this software code we write in LabVIEW. Then after that, we place the whole of the code in this USRP device. So what a USRP device does, it generates an FPGA code. So that is equivalent to hardware relevant code. So it generates a modulator, it generates an encoder, it generates a communication system. So then after that, it gives that output to an antenna is available. So it radiates into open air. That's what we proposed in our laboratory using a PAM modulator. So look at the diagram. Look at the diagram. So there are two pieces. For only photographic picture we placed side by side. Otherwise we have placed these two workstations at a 10 meters distance, like this hall. One is a transmitter, the other end is a receiver. So look at the first one. The devices what we used are USRP. Can you see the USRP? I am making a tick mark. USRP, Universal Software Radio Platform. So this is an NI device. And another USRP as a receiver. One USRP as a transmitter, another USRP as a receiver. Okay. So we have done our modulation scheme, encoding, your Hermitian symmetry, everything in your LabVIEW. LabVIEW is a National Instrument software. So we have written the code in one PC, and so from that PC it is connected that output to your USRP. So in the USRP, generally at these two locations, we will see, look at the USRP. So this USRP is connected with RFA, one is transmitter and one is the receiver, right? So this transmitter output is, if you see the output at this place, it is generally has an antenna. But what we did, we removed the antennas. We removed the antenna. We connected with a driver circuit, that is a bias T. I told we have to add a DC bias, right? So for DC bias, we have taken, can you see the 3-terminal device? The 3-terminal device takes 2 inputs and give 1 output. What are the 2 inputs? One code is written on software that is dumped onto the USRP. The USRP output is connected to this bias T. The another value is a DC voltage. A DC voltage is connected from RSP, regulated power supply, right? So these two, that means from USRP we are getting a sinusoidal signals, AC. To that AC we have added a DC, so that it makes always positive. That voltage is given to, using a driver circuit is also connected, so that the switching mechanism of your diode make sure that it takes all your signals within the limited range of cut in and cut off. Okay. Then we have just taken one LED lamp. From that LED lamp, we have just taken one LED out of it. There are many LEDs available in this lamp. We have just taken one LED, a sample LED. So that is the where you could see the globe. The blue color glow is your LED circuit. LED. Okay. Now, receiving. For your receiving part, for us, there is no option. We have placed the receiver at a tripod. That is a photodiode is your receiver. Photodiode is your receiver. Then the photodiode output is connected to USRP. Can you see that? The output is taken from USRP, and photodiode also need a regulated power supply because it needs a bias voltage. So it's connected to bias and it is connected to USRP. At the USRP output, so decodes, again converts into a software platform. The software output is taken onto the National Instruments LabVIEW. Then we coded everything to demodulate your signals. So you could see this is an amplitude modulation scheme on positive side and a negative side. Okay. So this is the experiment we conducted at our laboratory. So we could see the output, how the output is coming of in-phase data and out-of-phase data. So with a certain delay, the output is coming. Why there is a delay in output when you are receiving it? Can you guess? The travel time taken, right? And also device, some delays are there. So this delay, there is some amount of maybe 0.00 1 or 5 minutes, milliseconds delay is there. So now when you observe the output, I cannot decode the signal exactly. Why I cannot? Because my decoder always looks at some window. So in that window, where I am receiving after this time. Right? So even the second pulse also will be received after this time. I'll place the window at this point. But the partial portion is going out of the screen. So what we are supposed to do, we have to create a synchronization mechanism. What is that synchronization? The time taken to receive the signal, we have to estimate. So this have to be estimated, how much time it taken for receiving your signal. So that time I will fix at the receiver. From that time onwards, I'll make my window, I'll observe in this window. I'll observe only in this window. Okay. So during that window, I'll observe and I can decode the signal. So that much delay I have to decode. So how do you estimate this time delay? This is another technique. So we introduced, so many techniques are available. So out of those available techniques, we have added one more technique to that, gave us a good publication in Q1 journal. And so we have introduced the estimation techniques and we have deployed. So generally, for undergraduate student, how do you do this estimation? I'll give one example. Okay. Okay, I can draw over here. So I am receiving a signal. Let's say for me, I'll just a rectangular signal. I am assuming that I am receiving a rectangular signal. So there is some delay. So we have to estimate this delay. Right? So then after estimation, I'll make a correction at the receiver. So I'll see that my window will start after this time delay only. So in general scenario, nobody will give you how much delay is coming at the receiving end. But we have to use a technique to establish what is the amount of delay is available. A general procedure is correlation. You know the correlation? What is the correlation between two signals? I have a signal x of t, I have a signal another x2 of t. How do you compute correlation between two signals? If they are real, no problem. Otherwise, I have to make a conjugate. This is the correlation between two signals, right? Suppose I have a signal, one signal. I have another signal. What is the correlation between these two signals? Just multiplication. Suppose it is a value of 5, value of 5. Multiplication between these two signals, what is the amount? And multiplying and also integrating. Is nothing but adding. Integration is nothing but adding. So 5 multiplied by 5, how much? 25. And each sample, at each sample, it is 25. So I am summing up. So when you sum up, what you will get at the output? A correlation value. So when you are adding 25, 25, 25 like that, so at the peak, I'll get a maximum value. That is nothing but your max filter concept. Max filter is also correlated, right? It functions on correlation. So now this middle and Cox algorithm, this one algorithm is available. So what we will see, we are receiving a signal. What is middle and Cox and other authors are saying, keep your window, some window, and keep on moving this window along the waveform what you are receiving, right? So when you will get a maximum output, when you are moving the window, when that window is exactly placed on the receiving signal, according to the principle of your correlation, this is my correlation, right? Where you are getting the maximum value is when both of them are on 1 to 1, right? So when you are moving along this direction, so when it is placed on above top of it, I'll get a maximum value. That means how much movement I made. I made this amount of movement. That is my delay estimation. So we do a lot of math to establish this concept. So the delay estimation, we do the delay estimation, we'll fix that estimation when you are receiving the signal. So from after maybe, suppose that estimation is 1 millisecond or 1 microsecond, I'll fix my window after 1 microsecond only, I'll track my output signal. Okay? This is a very useful area of research in communication. The synchronization issue, one of the most critical issue in your communication systems. So we adopted some synchronization issues and also we did, so here we did for a QPSK signal. Can you see that? Quadrature phase shift keying. That means 2 bit at a time I transmit. So we receive those signals. So if any student or any faculty is interested in visible light communication, there is a 25 pages paper is written by my student. So you can see it is a survey paper. It is a survey paper. You can see all the concept of your visible light communication, what the reviewers or researchers have done. We made a contribution to that, and it is came into a very good publication in IEEE Sensor Journal. So you can see visible light communication concept. And also, if you are interested to work on visible light communication, there is one textbook available written by 3 authors of women. Myself, my student, and a foreign collaborator. So, Sushila, Mani, and Mathini. So, 3 authors. Mathini Salatarai, she is a professor at Harriet-Watt University. So, we made a very good contribution to the visible light communication. We have written a book on visible light communication. So, I can show that. So you can verify our research in my Google Scholar citation. So also we are working with RIS. Yeah. So visible light communication, comprehensive theory and applications with MATLAB. Also you can find MATLAB programs are also included. So this is a textbook. It's available. Maybe you can recommend to your library. So you can adopt this book for your small projects. A simple project can be using basic mathematics, very simple mathematics, not of use mathematics. So you can use this book for your project work because many MATLAB codes are also given in this book. Visible light communication book. You can make a photo of it. Right? Taken? And also other research what we are doing, I don't know whether it is, we are doing with RIS, reconfigurable intelligent surfaces. I don't think it will open here. So RIS with energy harvesting, and also we are doing the same what we did for the real-time communication. So we made our own IRS module, and we designed a control circuit, we designed a antenna cells, unit cells, and we made it for fabrication. Now we are testing in real time with the addition of reconfigurable intelligent surface, how the system performance is going to increase. So for the undergraduate students, I just give a overview of what is RIS, reconfigurable intelligent surface. So we are sitting in this room, right? And everyone want to access a Wi-Fi, but we are maybe the nearby surrounding areas, there is no base station available. So the signal is very weak. So we are not receiving a very good signal in your mobiles. Okay. So what is the other alternative technology, or maybe when you are going for your pleasure trip to any peaks like hill area, so when you go down of the hill area, because of the obstructions from the hills, we are not receiving any information. We are not receiving any signal on your mobile phone. But how to extend the signal? So the new concept has come up. So we can keep one relay system over there, but maintenance of the relay system is taking lot of investment we have to put on your relay systems. Instead of that, we can attach a simple a patch antenna type of a reflecting surface like this, and we can place it on top of the hill. You can place it on any building or any tree also. You just patch it. So this is a reflecting surface. Just you patch it to any board or any wall. So what it does, this reflecting surface is the signal. Some signal is available on the top of the hill. So that signal falls on these surfaces. So then the surface is made such a way that it is also connected with a circuitry, where the circuitry takes that the signal goes towards the down of the hill. So like we make a beam forming. So like a beam will transmit the signal. So signal is fallen on this place. The reflecting wave, we made it as a beam such that by alignment of these patches and also the tuning of these devices, which one to be on, which one is to be not on, such that we make this device circuit so that it makes a beam forming and it reflects the signal into a beam light goes into the down of the hill. So with this simple technology, we can extend your signals. So we can even receive your signals even if you go deeper into the sections, or a tall building is there where your objection. So there is a lot of obstruction. It will not allow the signal to pass other side of the building. Then what we do? Slowly we will place these RIS elements in several places such that this placement will accommodate your signal to transmit from one side of the building to the other side of the building. There is a new upcoming area where people are working on it, and it is also into the maybe adopted into 6G technology. So we are also working on into that area. And high mobility, when you are traveling in trains like Vande Bharat train, can you properly receive your signal? It's not possible because of your Doppler spread, Doppler shift. Your mobile is moving away from the base station, so the signal is also delayed to certain extent. Already certain delays are there. The further delay is added by your Doppler, so we cannot receive your signals properly. There is another technology called orthogonal time frequency space system, OTFS. So that is one of the technology where we made into clusters, like we divide the system into a two-dimensional plane. We take the three-dimensional into a two-dimensional plane. Delay is separate and Doppler is separate. We combine both of them into the one domain so that we can eliminate this Doppler shift. Okay, that is one of the area where we are working on it. So a low complex wireframe based PCO OTFS modulation for visible light communication system. This is one of the paper where we are working, and also real communication also we did. So OTFS system based on, so here it is, because IEEE is not connected to you, so you could not see, otherwise it is a Q1 journal. OTFS system based on WFR, FTOFT with optimal design complexity. So it has a lot of mathematics in it. It's not opening. And my student Malaya currently is doing his postdoc because we don't want to go abroad for postdoc position. He's more of a homely fellow, so we don't want to leave his state. That's another problem. Otherwise, he had many opportunities, and so he did with OTFS system with optimal design complexity. So finally, I am concluding my talk, and I want to give a very useful information to the students. So suppose if you want to continue your education with NIT system, because somehow you are with Narsaraopet Engineering College only, right? But you want to see how the education system is different at NITs and IITs. If you have a wish to continue your degree, higher degree at NIT Warangal, we have an option in your BTech final year. Suppose you have achieved a CGPA of 7.5, you can convert into your percentage, I don't 70%, right? So that is equivalent of 70%. If you are having, we'll conduct one national test based on a GATE syllabus. So if you qualify in the test conducted by us, you will be given a stipend. You can join with us for a full-time PhD program without master's degree, without MTech. Directly you can join for a full-time PhD program. The program, the scholarship will be given for 5 years, but you can complete within 3 years also. If the student is caliber and he is very interested, he can even complete within 3 years, 3.5 years, 4 years. That depends upon the caliber of the student. So what we teach him the MTech courses. He has to do the registration with MTech courses. It's not like he did not do his MTech. That feeling is not there. He has to do all the MTech courses. Soon after the MTech, he need not do any thesis work. So his thesis work starts with the PhD thesis. That option is there for all engineering graduates if you are wishing to continue your higher studies. And there are many options available at NIT Warangal because we have a campus placement. So to take our students even with PhD, with MTech, with BTech, so there are many options are available. You can sit for our placements, and they take the PhDs are also absorbed uh, into companies. So we have three domains: VLSI, embedded systems, and communication systems. I belongs to communication system because my whole of my work is only talks about mathematics. And also we do experimentation. The new addition to my research is experimentation is another research. We are very thankful to the National Instruments. They are providing a device because otherwise we cannot